start recording. And today we're going to go on speed. So I know I like to typically answer your questions as we go, but if it's not completely like pertinent to something that's, you know, being discussed right now and it's like a big ticket item, let's kind of hold that off until maybe the end of the period if there's some time that we can ask those questions, because we do want to get through all of chapter 7 and it's to your benefit so that you guys can, you know, have this session before the test. Okay, so if you guys are following along, the warm-up question we're going to do today is on page 70, and it's number 13. So page 70, number 13, if you guys care, and I'll reproduce it below. So we're starting with what looks like this center starting material, and we need to kind of just navigate this roadmap. So basically what it says up here with this top arrow is we have Br2 and methanol, okay, and it says A. So basically, this is asking you to draw the products that result from subjecting this alkene to those two reagents. Okay, so what does this look like? We kind of haven't seen this one before, but this is actually just a version of halohydrin synthesis. Remember, we know how to do, remember with acid catalyzed hydration when we said we had this arrow and we did water and acid, okay? And then we said, okay, there's another version of that. Instead of water, I could just do maybe an alcohol like methanol and catalyze it, and the resulting structure was instead of maybe like an alcohol, we formed something like maybe an ether. Remember that? So, and this would be from, you know, that starting material, but essentially this was the variation that we saw. We could change water to methanol, and instead of a proton coming along in the functional group, we got kind of this R alkyl group, okay? So the same thing happens here. So instead of forming a halohydrin, you're actually forming a haloether. Okay, you guys can see that. So instead of the hydrate, you form an ether. So this is going to be a haloether, essentially. So quickly, I'll just draw that, you know, bridged intermediate. And remember, it's racemic, so don't yell at me about stereochem. So I'm just going to draw, you know, quickly with no stereochem in here. You know, that's the bridged intermediate. And remember that methanol attacks the more substituted position for the reasons we've already talked about, meaning resonance. So you can imagine that the methanol would attack here and open up the bridge there. Okay, so the resulting structure would be, you know, maybe a benzene ring, okay? And then let's say if the bromine bridge was already on a wedge, okay, that means that the methanol had to come in on a dash, okay? And then that means that the existing methyl group that was already there has to be forced onto a wedge, okay? So that's the first kind of structure that we have going on, okay? And then after that, we have the other kind of major stereoisomer that we have to consider, and that was if the bromine was already on a dash, okay, that means methanol had to come in on a wedge, because remember it's anti-addition, and then that already existing methyl group had to be forced on a dash, okay? So that would be the, you know, products of A. So instead, we still see anti-addition with respect to, you know, the ether and the bromine, but instead of it being a halohydrin where it's water and bromine, it's an ether and bromine, okay? So I don't think anything too crazy. Yes, it's a little bit different than what you're used to, but nothing too crazy. Okay, so for this one, we're seeing we have what looks like hydroboration oxidation conditions. We've talked about that last class. So we have borane and that inert solvent THF on the top as step 1. And then step 2, we have that source of the alcohol. That's the hydroxyl group. And we said we don't really know what H2O2 does. Okay, so we don't have to worry about that. So for all intents and purposes, you're kind of just focusing on BH3 and sodium hydroxide. Okay, so remember what happens is this is the anti-Markovnikov addition of an alcohol. So if this is the tertiary benzylic position and this is the secondary position, it makes sense that we're going to have an alcohol add here. But remember, this is syn addition with respect to the BH2 and the H fragment, okay? So that basically says, like, if I were to add, maybe, and I'll draw this down here. So that tells me that if I were to add the BH2 group to the less substituted position, like this, BH2 on a dash, I'm also going to do the same thing with the other H fragment, okay? So maybe you can see the resulting structures from that. So clearly, we're going to have a hydroxyl group that, so let's just say they come in on the dash first, okay? So they come in on the dash, that means that this methyl group gets forced to a wedge, and then that's going to mean that this alcohol, okay, was on a dash. Okay, do you guys kind of understand that? So what happened is that it's the BH2 and the H that were both added on dashes. So for all intents and purposes, you can draw this H to see that it was syn addition. okay? And then, that second step replaces the BH2 with the OH, okay? So that's the first one. And then you can kind of imagine, what if they approached on the wedge face of that pi bond, okay? So if they approached on the wedge face of the pi bond, so let's just do something like this, maybe wedge and wedge. Okay, that forces this methyl group as a dash. Remember, that was a wedged hydrogen. And then if that was coming in on a wedge, then that means that this should also be on a wedge, okay? So with respect to the hydroxyl group and the proton, yeah, they're both syn addition, but it forces that other methyl substituent onto the opposite configuration, okay? So that is, B. Okay, so for C, we're going to do what looks like a catalytic reduction. So we're going to subject it to hydrogen gas and one of those transition metal catalysts, so platinum, palladium, and nickel. And we said that this was also syn addition, okay, syn addition of the H2. Okay, so that means that both of them are going to be added on the same base. So kind of let's draw that same, skeletal framework of the sigma bonding. So you can imagine that I would be adding hydrogen here on a dash and then maybe hydrogen here on a dash. So what does that do? Well, it doesn't do anything in terms of stereochemistry for this, terminal methyl group or whatever, but it does affect the methyl group here. So, a major stereoisomer from this structure would be the methyl group as a wedge, okay, so chiral. And then let's say I added it on a wedge instead. So if I added them on wedges, it forces that other group to be a dash. So these would be my two main stereoisomers, okay? And I'm doing these fast because at this point, you guys should know all of chapter 6. That's what I told you guys on Monday. You should know all of chapter 6 pretty good by now, okay? So that is A, B, and C. I hope you guys are kind of also taking note of the consequences in terms of stereochemistry. So here it looks like we have ozone as step 1, and then 2 I'm going to abbreviate as DMS, so that's just dimethyl sulfide. It's kind of what you see. And we want to draw the products of that. So that was easy. This one was simply just cutting, okay, and then drawing the 2 fragments and then putting the carbonyls there. So let's call this fragment A and let's call that fragment B. So for fragment A, it's just this, and I'll draw the proton in. So see, for fragment A, it was just this part. So that's the methyl group to the right, the hydrogen not drawn in, and then the pi bond up top. So that would be the methyl group to the right, the hydrogen to the left, and then where that pi bond was, where we cut, because see, we cut that, you just put an O. Okay, so that's the first fragment. And then you also get the other structure. So it would look something like this. Okay, so all I did was cut where that pi bond was, and then where my finger is, I put an oxygen. Okay, so you would have this benzylic ketone, and then you also have acetaldehyde. Okay, so you get these 2 major products. Okay, so that's D. Okay, so for E, okay, where it looks like we're subjecting this to osmium tetroxide conditions, and we went over what each of these reagents does. So we said that osmium tetroxide adds in this like concerted mechanism to form a syn diol, meaning a diol is 2 alcohols and syn meaning the same face. So this was again another example of syn addition. Syn addition. Okay, we knew that water did this hydrolysis step to form the diol, and then hydrogen peroxide is just there to regenerate our catalyst. It does an oxidation step, but you don't need to know the mechanism beyond the concerted step. So essentially, you get something that looks like this, and you get so if the hydroxyl first comes on a wedge, that forces that methyl down. And then you also get a wedged hydroxyl, and this methyl can stay the same. And likewise, you can draw the dashed version. Okay? So syn addition with respect to the diol. Okay? And I think we have one more step. So the next thing we're going to do is subject it to HCl. Okay, and see what happens from that. So this is the first reaction, pretty basic. You're going to get a tertiary carbocation at that position, and then you're going to have subsequent, attack with that halide to form, a haloalkane. So essentially, we're talking about our tertiary benzylic intermediate. So that would be a carbocation there, and then Cl comes in. So I'm going to erase that Cl, and you have to consider both major stereoisomers. So this wedge dash version, and also wedge chlorine dash methyl. All right, so that's pretty much how you do all the chapter 6, the main chapter 6 reactions. I know I may have left a couple out, like oxymercuration, a specific halohydrin, things like that. But for the most part, if you were fine with this web in terms of getting the major stereoisomers, you're going to be at least 50% good with your test. Okay. So anybody have any questions on the old chapter 6 stuff before I move on? Madison, do we specifically have to know the names of the reactions? Like, no, like you don't have to know, like if you don't know oxymercuration, demercuration, but you're able to recognize the reagent, or if you're able to recognize it kind of, that's okay. Like we're never gonna be like, what's the name of this reaction? We're not gonna ask that. But you might have to be able to recognize in a question that says like, draw the products upon subjecting this to oxymercuration conditions. You know what I mean? So you kind of have to be aware of what they are. How could they ask mechanism? That's a great question. My guess is Dr. Peterson and Dr. Habenecht are going to have answer choices already, like 4 answer choices with pushed arrows in them. So like A and then B and then C and then D, and then maybe she'll show this example, and maybe she'll show this example, and then different versions of the arrows, and then you would be able to pick that. Will we have to fill in the missing reagents or conditions? Yes, absolutely. You're going to have to go backwards. So there'll be situations where you'll have this product and you'll have to draw the starting material. There'll be situations where you'll have the product and the end product, you'll have the reagent and the end product, and you won't have that. So you have to know everything. It's not just one way. You have to know product to reagent, reagent to product, maybe sometimes putting that mean reagent in there, things like that. I wanted to write this web. Yes, and I can zoom out in a second, Hayden, and this is a private message. And again, okay, so my biggest pet peeve is really asking about when these videos are going to be uploaded. So I get emails literally every day about that. Like, you guys know I post them like pretty much right before that weekend, before your exam. Today is going to be one of our last sessions, so I'll try and get them all up today, okay? So that's that. And then here's kind of a bigger macroscopic view of, if you want to screenshot this real quick. Okay. Sorry, I'm shaky. It's hard to hold my phone. Okay, hope you guys got that. All right, so we're gonna move on to chapter 7 stuff. We have a lot to cover. Sorry if I'm going psycho crazy fast. But essentially that's pretty much it for chapter 6. So you guys should be good here. Now in chapter 7, we're going to extend a lot of the reactions we saw with alkenes and just vary them a little bit to alkynes, okay? So this shouldn't be as hard as, chapter 6 was to learn, but there are some key steps that we're gonna talk about, okay? So I'm not gonna go over nomenclature. I think that's pretty, a big waste of time considering it's just following rules. So you guys can just practice the nomenclature on your own. But the first reaction we're gonna talk about is something called acetylide addition. Okay, so number 1, reaction 1, and we are in chapter 7 now. Okay, so alkynes. So moving forward from, at least where we are right now for the rest of the time that you're in Orgo 1 and 2, is each chapter is going to get a functional group. So you saw 6 was alkenes, 7 is now alkynes, 8 is going to be radicals, and so forth. So you're just basically going to do this for the rest of your time in Orgo. Each chapter, you get a functional group, and you subject it to a whole bunch of reagents, know the mechanisms, know the products, and that's pretty much it. So if you like this stuff, you're in luck, because I like this stuff too, and honestly, it got a lot cooler in Orgo 2 because it's applied to your body. So I don't know, just prefacing that. So reaction 1 is acetylide addition. Acetylide addition. This is a very, very important reaction, especially for synthesis, and we're going to talk about why, okay, in a second. So essentially acetylide. So what does that mean? So essentially we're going to just draw a generic alkyne, okay, and specifically I'm drawing a terminal alkyne. It has to be terminal, and we'll talk about why in a second. This is a terminal alkyne, and we are going to subject it to this reagent known as sodium amide. So sodium amide, that's this guy. And then we're also going to have a solvent again, okay? So this isn't a step 1, step 2 situation. This is sodium amide. This is my main, nucleophile that we could arguably, say is also a base, and we'll talk about that why in a second. And this is my solvent, ammonia, okay? So this is ammonia. All right, and you can see why we use ammonia as the solvent, because it's pretty similar in terms of, chemical arrangement like sodium amide is. So it's a pretty good solvent for dissolving that nucleophile without losing nucleophilicity. Anyway, so if you go back to acid-base chemistry, so chapter 4, we had a trend. So I'm going to just draw this out. Actually, Let me draw that. Okay, so this is 1, this is 2, and this is 3. Okay, so I'm asking you guys this question. Out of structure 1, structure 2, and structure 3, back to acid-base chemistry, put in the chat box which one is the most acidic. Okay, 1. Thank you, Madison. Thank you. See some more. 1. Yep. 1s, a lot of 1s. Okay, so the consensus is 1, and that's great. You guys remember your acid-base chemistry. So our trend for that was, remember, as percent S is increasing, I guess that's a bad arrow for saying, maybe I should just do percent S increasing means we increase acidity. And we don't need to go over that trend again and why, but remember that the S orbitals are closer to the center of that sigma bond framework. So let me just draw an example. So S orbitals would be there. P orbitals would be a little bit higher in a way. So as you increase the S character, which we do with, from alkene to alkene to alkyne, you are, more electronegative. Remember, we can use that more electronegative. And remember, we said if it's more electronegative, it's definitely more acidic. So something that we're going to do with this terminal alkyne is we are going to manipulate this acidic proton and then just do a simple acid-base reaction. So remember, we said back to, acid-base chemistry was these ammonia type, groups, these amines and amides, those are pretty basic species. I don't know if you guys remember that. So we have a base, nucleophile / base, and we have an acid. So you can imagine the mechanistic arrows would be the lone pair of the sodium amide, okay, grabbing that proton, and you know that the electron density is going to be retained on the carbon because, there's a slight dipole, in favor of that, alkyne. So the resulting structure is this acetylide anion. So you just put a negative charge on that carbon of the alkyne. So this is called the acetylide anion, okay? And this is huge. This is a really important reaction. That's why I'm going so slow, okay? So that's step 1, okay? That's the first part, okay? So what we just did is we generated this, new nucleophile. So this is the first time that we're generating a nucleophile. So it's weird. So in step 1, we had an acid-base reaction, and that was it. So it was just sodium amide deprotonating that terminal alkyne for reasons we've just talked about over here, okay? And then you generate this nucleophile, okay? Is anybody confused or want to ask anything up until this point? Awesome. Okay, so that's the first step. And then the second step is typically you're going to take this acetylide anion, so something like this, okay, and you're going to subject it to some sort of haloalkane, okay, so let's just call it X, okay, so this X could be, bromine, chlorine, iodine, any of those guys, okay. So what happens is we're going to use the same logic that we've always been using. So, let's rationalize our dipole moment. So there's clearly a dipole moment in favor of that halogen, right? So we're partially negative. That makes this carbon partially positive. Do you guys see a potential reaction happening here? Okay, yes or no in the chat box, right? Do we see a potential reaction happening? Yeah, right, great, that's good. That means you guys are getting the logic. A negative thing likes this positive thing. So that means that we're probably gonna draw an arrow from that negative to that reactive center, which is that carbon. Remember, there are already 2 protons here, okay? So we do exceed the octet by forming a bond there. So that last step is to break the bonds between that carbon and the halogen. And then the resulting structure is actually a longer carbon chain. So if I were to number, we have 1, 2, 3, 4. Remember, that's the 4th carbon. Don't forget that, okay? And then we're adding what seems to be 2 more carbons. So it looks like 5 and maybe 6. Okay, you see that? So essentially what that end product is going to look like is a 1, 2, 3, 4. Okay, so 1, 2, 3, 4. You have to always number these because you don't want to drop carbons. 5, 6. Okay, so this is my end product. Okay, how interesting is that? So this is the first reaction and the only reaction, this is why it's so important, that we know of at this point that is going to make a carbon chain bigger. Okay, if you're sleeping, this is the biggest thing, and I'm going to tell you why, because it's going to be tested like the last 2 questions of your test. Okay, you need to know this is the only reaction at this point that to add carbon chains. Okay, so I'm sure you guys kind of know what synthesis is. Okay, it's really important for synthesis because if you see somewhere in your synthesis problem that you are adding carbons, you have to have gone through this step somewhere. Okay, And that's going to help us when we get to that point, I think, later today. All right. So that's acetylide addition. Okay. Really, really one of the most important reactions in Orgo 1. Okay. Any questions? Great. Okay. Let's do a couple examples of those. So we're on page 75, letter A. Okay. Page 75, letter A. So hopefully you guys are going to catch me on these examples. So it specifically only works for terminal alkynes. And I think we've kind of proved that, because if it's internal, you don't have this proton to, manipulate. So step 1 is this. Step 2 is going to be, it looks like a propyl. So 1, 2, 3, that. So I just drew that out in line angle. Okay. And we are going to see what happens here. So, step 1, like we said, is going to, do the acid-base reaction to deprotonate that terminal proton and then generate my acetylide anion. So we've seen this already, okay? And then what's gonna happen is we know there's a dipole towards that bromine. So we know there's a dipole moment towards the bromine. So we get a partial positive at that carbon. So the next mechanistic arrows would be this lone pair hitting that reactive center. We know that we have 2 protons here, so we exceed the octet, and we need to break that final bond, okay? So the resulting structure should be something with 1, 2, 3, 4, and it looks like 5, 6, 7 carbons. So 1, 2, 3, 4. So this is 1, 2, 3, 4, 5, 6, 7. 5, 6, 7. Always count. It's like you can't. I still do this, and I'm 2 years, 3 years removed from Orgo 1, and I still count it. Okay, so just do that. Okay. So here we are. All right, so that's A, and then let's do B. So B would be something similar. So we have this. Okay. And we are going to subject it to the same reaction conditions we've seen above. So sodium amide dissolved in ammonia, and then we're going to subject it to what looks like benzylic haloalkane. So that would be something that looks like this. Okay, so again, we know I'm not going to draw the mechanistic arrows. I think we're good at this point. So the main key intermediate is this carbanion, not carbocation, carbanion. And so we can call that a carb anion. So not a carbocation, this is a carb anion, a different intermediate. So that, negative charge is going to attack that reactive center. So if you count, we are 1, 2, 3, 4, 5. We're adding 6 and the benzene ring. Okay, so that would be 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Here is 6. Okay, so that's 6. And my benzene ring. Okay, so you have to say, I always speak to myself, when I'm actually drawing these out. Okay, I know I need 1, 2, 3, 4, 5. I'm adding 6 in the benzene ring. And I kind of say that over in my head. And I do, okay, 1, 2, 3, 4, 5. I need 6 and the benzene ring. And it produces itself very nicely. I know it seems weird to talk to yourself, but 100% I think that's helpful for these. Is the lone pair to carbon or negative to carbon? Is it lone pair to carbon or negative to carbon? It's both. The negative is associated with the lone pair on that carbon. So yeah, on my computer, I'm on my phone. Steven, could you let me in on my computer? I'm on my phone. Yeah, I don't see that. Are you in the waiting room? I just tried to let you in. I hope that worked. And yes, thank you, Abby. I dropped that. Don't do what I just did. There's a methyl on 2. Don't drop those things. And let's see, for practice probs, do you recommend we write out the entire mechanisms, or should we practice showing the products like the exam? Okay, Abby, great question. Everybody listen to Abby's question. So I would definitely write the mechanisms completely out in their entirety. I would just see this one and maybe draw the full mechanism out. You can pick any take any question from the student workbook and make sure you can do at least one of each mechanism. Just do one. If you can do one without looking anywhere and you understand the chemical logic, fine, move on. That's fair. They're not hard. I don't think they're so hard, especially at this point. In Orgo 2, you get mechanisms that are a full page long. Okay, so this is not bad. The 2 steps. So I do recommend though that you are able to do what I'm doing. Quickly, what's my main intermediate? How do I go to that product? Because you're not going to have the time, seriously, on these exams to go through every mechanism on every problem that you see, especially with multiple answers like you have with the multiple choice. So you need to just know how to do these like pretty quickly, jumping around in your head. Okay, so that was B. We'll do one more example and I'll move on. Okay, so let's just do C. So C looks like, cyclohexane with, I'm just going to draw it down here because I'm running out of space. So we have this terminal proton. I'm going to say sodium amide. Okay, dissolved in ammonia. And step 2 is going to be this weird haloalkane. Okay, so we know our main intermediate is going to be this acetylide anion down here. Okay, it's going to attack there. So we're going from, a 1,2 substituent. That's what I'm going to call it, a 1,2 substituent. And we're going to 3, 4, 5, 6. Okay, so my end product should be, this is my 1, 2, 3, 4, 5, 6. 3, 4, 5, 6. And that's your product. Okay, that's enough for acetylide addition. Let's move on to our next reaction. And this is going to be kind of the opposite. So whereas before we were using, we were using haloalkanes kind of as a reagent to extend the carbon chain. Here we're going to start with a haloalkane and we're going to go backwards to an alkyne. Okay, so essentially this one is called double dehydro. Oops, I didn't spell that right. Dehydro halogenation. Okay, and the name kind of makes a lot of sense. I know the names are really long, but it makes logical sense. So we are going to start with some sort of, haloalkane that is probably 2 haloalkanes. You can see double, we're doing 2 rounds of something, and we're dehydrohalogenating. So you can imagine we're removing the hydrogen and the halogens, okay? So that should kind of give you already a big clue of what we're doing. So I'm basically just going to start with the example of 11F or whatever, we're on F. Okay, and we have something like this. Okay, so clearly we have a double halogen. And more specifically, it gets this name vicinal. Okay, so if you care, like vicinal is a name for when they're adjacent to one another like that, like when the two, so it's a vicinal halide, essentially, a vicinal halide. They're adjacent to one another. And we're going to subject it to the same reagent that we saw above, but this is the first time that we're going to see something denoted in parentheses that we haven't seen before, and it's equivalencies, okay? And people get confused on equivalencies, and honestly, guys, it's just stoic. Like, remember, you would have like a 2 mole to 1 mole ratio of this, or a 10 to 1 molar ratio of that. So let me give you an example. Like, typically, here, we need to come up with a lot of the time in Orgo Lab, you'll see, we have to come up with a nice solution, to dissolve, so maybe to crash out some product, okay? So maybe we'll say that, I want, let's see, I want ethyl benzene in maybe like 50% quantity, and that's the, the organic layer, and maybe I want water to fill up the other 50%. So if I were to do that, that's a 1-to-1 stoichiometric molar ratio. So that would be 1 equivalent of each. But let's say, no, I didn't really want that. I wanted maybe 25%, okay? I want 25%, and maybe I wanted 75%. So clearly this is now a 3-to-1 molar ratio in favor of water. Okay, so that's really all it is. It's just the ratio of the ratio of reagent to starting material. So we have 2 moles of this to the 1 mole of that. Okay, so that's basically all it's saying. So you can write maybe 1 mole, and you can write 2 moles. Guys, I actually have to go to the bathroom, so I will be right back. So just look at this one and stare at it for like a minute. Okay, sorry, we are back. Okay, so where were we? So just talking about the molar quantities, okay? So that was pretty much all we left off with, 1 mole to 2 moles. So essentially, let's consider just the first mole of sodium amide. So we're just considering the first, quantity of it. So this would be equivalent to me drawing, that, and then the spectator ion is hanging out, okay? And let me just draw in the protons that are here as well, because as the name implies, it's dehydro halogenating. So maybe the hydrogens are gonna have something to do with it. So essentially the first mechanistic step is, remember, why are these protons acidic, okay? And remember, this is the acid-base reaction. So because of the inductive effect, remember, when we're close to these electronegative, atoms, we're able to delocalize that negative charge over a larger, region of space, which makes the conjugate base more stable. And if the conjugate base is more stable, then we're able to, do the acid-base reaction. That was kind of like the reason we all went through this. So that makes sense why, this sodium amide, which is a base, is going to grab that proton. This is very important. Watch this. So the carbon, hydrogen bond, we've typically seen that as putting those remaining electrons back as a lone pair. We're not going to actually donate them as a lone pair. You could, it's possible, but what's better to do is take those bonded electrons, push them in to form a double bond right there, and then that exceeds the octet and kicks off the fluoride. Okay, so this is another one of those like multi-arrowed mechanisms for the first step. So that is the result of using one full equivalent. So now we're left with one EQ. So the resulting structure after the first step was, or at least the first equivalent, is going to be something that looks like this. Okay, do you see that? So we did one round of dehydro halogenating. We removed the hydrogen, we removed the halogen. So that is one round of dehydro halogenating. But the name implies we have double, and that's why we have the second molar quantity. So does that all make sense now why we have equivalence? So the reason we have equivalence is the fact that we only have one of this to, let's just do the first mole of that, and that forms that product. And we would only get this product if we didn't say two equivalents. But now that I have a second round of that, I can do this reaction one more time, essentially. That's what it's saying, okay? So we're here, and the same exact mechanistic arrow. So now the lone pair is going to grab the proton, donate that electron density now to form an alkyne, okay, and then remove the fluorine, okay? So then we're left with, so now the alkyne is going to be between 2 and 3, so it's 1, 2, so 1, 2, 3, 1, 2, 3, 4, 5, so 4, 5. 4, 5. So you always have to count these, okay? So that would be the 1, 2, 3, 4, 5. And then that's the resulting structure of my alkyne, okay? So this is backwards, right? But I think all of this pretty much makes sense. So let's just do another example. Okay, so we're on, let's just do 11G. So we have, something that looks like that. We have a bromine here, and we have, looks like a bromine there. It's important to draw, oh, let me see the chat box. I didn't really look here. Let's see what's going on. I need more time. Today was new materials, Friday, the president also kind of heavy. Watch ASA, Monday would have been perfect. Okay, do to kick off the opposite halogen? Okay, yes, Abby, great question. It has to be the opposite hal. Thank you for answering that. It's always the opposite. So if we're moving this proton, you're kicking off the halogen over, not the one that's here. Same thing. If you're kicking off this proton, you have to kick off the opposite halide. Great question, though. The reason why it's that is because based on the mechanism, you're donating these electrons to form a pi bond, and you exceed the octet, and that forces this fluoride out because I guess you can. Oh, I see. Because if you're fine, you can argue that if you kick this one off at first, so you're left with a structure that looks like that, and that's fine. I mean, like here, how can you now do the next reaction? You're not going to be able to like remove this, push that in, and then also kick that off at the same position at the same time. There's too many electrons moving at once, and it's too repulsive for that actual mechanistic step to happen. But this is the more accurate way. Anyway, hope that helps. Emily, so if it was one equivalent, you are left with, yes. So as Emily says, if it said one equivalent, which we could trick you, please pay attention. We could write one equivalent, like on the test, and you would have to stop here, okay? But two equivalents implies here. So this is the one equivalent product. That's the two equivalent product, okay? Great question, yeah. Okay, so let's just do this example. So we're subjecting this to, okay, so this is a little bit of a different situation. So we have sodium amide, okay, ammonia, and for some reason we see three equivalents, okay? And then for two, we see water. This is very weird. You guys are gonna like not like me on this, but I'm just gonna tell you how it is. So we have the same thing happening. I'm just gonna draw this on speed. So essentially, the sodium amide is gonna grab the proton, donate that into the ring, push this proton off. Excuse me, not the proton. Didn't do that. Push the bromine off, okay? So after one equivalent, you're left with a structure that looks like this. Okay, so that's one equivalent. So this is one equivalent. Then do another equivalent, okay? So now the second equivalent is going to remove, let's just say this proton, push it in, kick off the bromine. Okay, so then after the second equivalent, you're left with a structure that looks like, how many carbons? 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. Okay, so let me just number that. 1, 2, 3, 4. I always number. You see, I'm just always trying to be cautious. So this is the product after the second equivalent. But we have a third one. Okay, so what could that third equivalent do in this situation? Well, that third equivalent is going to remove the only other proton I have, which is this one, okay, and do that. So the result of the third equivalent is going to be the acetylide anion that we saw at the beginning of today's session. Okay, so this is the acetylide anion. Really weird, honestly. I don't know why this is, and I literally have asked this every single year, and this is just the way that organic chemists do this reaction. They do three equivalents in step one, and then in step two, all water does, it's so weird. I don't even know why, but just accept it, and hopefully you'll remember me saying it's weird. It puts it right back on. So you're like, why did I just remove it in the last step? Why didn't I just stop at two equivalents? And why did I have to put it back on? I don't know. It's been a source of confusion. One of the things I just don't have a good answer to. So your answer is really still the step from above. It's just, we do this weird, removing that final proton and then adding it again. I don't have a good answer. Just remember to do it, honestly. Okay? I think it has something to do with the fact that we have excess base. So we do technically have this acetylide anion isolated after step one, and we don't want the anion, we want the neutral product, obviously. So that's why we have an acidic workup, just to add that proton back on. That's my one rationale, but again, I don't really have a good answer, and it's not really that important. Okay? Let's see, we got some questions going on. Emily, okay, hopefully you found us. Let's see, Andres, both are part of the final answer or just the two equivalents? No, just the two equivalents one would be part of that answer up here. Good question. Okay, assume completion, assume it went to completion. Roxana, does it matter which one you attack first? Absolutely not. Priyal, is the third equivalent the carbanion one? Yes, the third equivalent is the carbanion one, that's great. Is the water the third equivalent one? The water, so basically this is the product of the first equivalent. This is the product of the second equivalent. This is the carbanion is the product of the third equivalent, and then this is the result of step two. Okay, oops, I wrote that twice. That's step two. Does that make more sense? Hopefully, Brian, let me know. Vicky, are we ending up with a smaller chain? No, we didn't end up, in terms of carbon count, no, we are not going down in number. No, we are not. In terms of like heteroatoms, yeah, we're losing 2 heteroatoms. So in a way, yes, a little bit, but we're really, when we talk about chains, we're only referring to the carbon count, okay? Hopefully that helps you. Okay, here we go, let's keep moving. So I think that's enough for that question, but I want to move on to, what time are we at? Oh, geez, okay. Sorry guys, we're just gonna keep pushing. 11I, I feel like you guys would want me to just keep going, even you guys don't care that we go over, I hope. Is that the general consensus in the chat box? Do you care if I go over? Like, it's the only way I can cover all this. Okay, yeah, you guys, that was so fast. You guys are like, do whatever you want, please, please, you're funny. Okay, so here we go. So we have this structure. Step one is sodium amide and dissolved in ammonia. That's 3 equivalents, okay? Step 2 is going to be ethyl bromide. So I like to draw the line angle. I think it's better. 3, whoa, okay. Step 3, we're getting complicated. Step 4, DMS. Okay, so this is what I mean where like we can start making it more complicated. As you know, what looks like 3 and 4 is ozonolysis. So what we're gonna do is we're gonna compound alkyne reactions with alkene reactions. It's pretty interesting. Okay, so the first thing that we're gonna do is just do step 1. So we know the 3 rounds of equivalent, okay, is going to generate the acetylide anion, right? So I think we can just go right to the acetylide anion because we've done so much practice with that. So this is a 1, 2, 3, 4, 5 carbon chain. And you know that alkyne or that acetylide is going to be between 4 and 5. So if you can draw quickly the result of step 1, it would be 1, 2, 3, okay. And then let's just do that. So 1, 2, oh, my bad. 1, 2, 3, gotcha. 4, 5. Okay, and we got rid of that terminal proton, so it's that. 1, 2, 3, 4, 5. You see, it takes me multiple times to even get these structures, like, and that's okay if it's taking you multiple times. You just want to make sure everything is right, your carbon count is right, everything's placed. Like I knew the alkyne is between 4 and 5. I better make sure that my alkyne's between 4 and 5. It's okay if you mess up. Just make sure that you get your numbering and positioning of all the functional groups right. Okay, so we're here. Step 2 looks like we're just going to extend the carbon chain by maybe 2 extra carbons. So the product of step 2 is probably just the same thing we see. So let's just kind of fill that all in. So this was 1, 2, 3, remember 4, 5. So now this is maybe 6, and then that's 7. Okay, so now that's the result of step 1 and step 2. Okay, so everybody kind of following? We didn't really do any new things yet, step 1 and step 2. But now we know we have ozonolysis conditions for step 3 and step 4. But we know ozonolysis was only applicable in chapter 6, and I don't know anything with alkynes and ozonolysis. So clearly we're only going to react at this alkyne. So remember what I told you guys. You were going to, put a line through there, and you draw both fragments. So this is fragment A, fragment B. Okay. So what I'm going to do is the first fragment. So for fragment A, it's clearly going to be formaldehyde. So formaldehyde is this structure. So you generate formaldehyde, and this is the 2 protons that you don't see. Okay, that's the formaldehyde. Remember, you cross halfway through and you put an O where your hand is. Okay, so that's what I have here. And then for fragment B, it's the same thing we have. So, okay, so that's that. And then just draw the carbonyl. So this is an aldehyde. So these would be my 2 main products of that reaction. Okay, so we can start compounding old things to these new reactions. Okay, so you have to know everything. Okay. Anybody confused? I think this is still pretty obvious. Okay. I think that's good. I think that's good. All right, so let's move on to the next reaction. Any questions? I'll leave it there. Any questions? Great. Okay, so so now this is what I was saying, how like, if you know your chapter 6 reactions pretty well, you're gonna know your chapter 7 reactions pretty well because it's really just a little bit of an extension of what we've seen. So the next reaction is called halogenation of alkynes. So we know how to halogenate alkenes. So now we're just gonna basically do the exam. See you, Abby, good luck. Now we're just gonna do halogenation of alkynes. Okay, so we know how to do halogenation of alkenes. We're going to do alkynes, so let's just kind of review that. So let's just say we have HBr. We remembered that this follows Markov-Nikov's rule. We're going to generate a carbocation at the more substituted position, and then the bromine comes in and attacks there, and we had some potential stereochemical things to consider, but for all intents and purposes, this is kind of where we were for alkenes. Okay, so we're going to do the exact same thing for alkynes, and that equivalence thing could also come into play here. So let's just kind of take an example. So let's look at 11K. So we're here, and we are having a structure that looks like this. Okay, and we're going to subject this to what looks like Br2. And oh my God, I'm sorry. I didn't mean to do this above. This is hydrohalogenation. I meant to do the Br2 guy. I'm sorry. So let me just emphasize this again with you guys. So my bad, but good review anyway. So remember, this was the concerted mechanism, halogenation, not hydrohalogenation. And remember, the nucleophilic pi bond grabbed the bromine. We exceed the octet here. We developed a partial positive at the other end of the alkene. So that made sense why we formed this halonium bridged intermediate, remember? So I'm just gonna draw, just to remember that this was, the main intermediates. And we also had the other one, so the racemic enantiomer of that. And remember, we said that the bromide anion was going to add at the more substitute position for reasons we've discussed. And you got kind of this vicinal halide structure, remember it was anti-addition. Okay, so we're like there. Remember, so that was kind of the mechanism for halogenation of alkenes. So it's the exact same thing going on for the halogenation of alkynes, literally. So this is basically Br2, CHCl3. Anybody remember the common name of this, CHCl3? You guys want to put it in the chat box while I'm writing this out? Anybody? CHCl3, it's something cool to know. Oh, not ethanol. Chloroform, it's chloroform, remember? So DCM is dichloromethane, so that would be CH2Cl2, that was DCM. And then this is the chloroform guy, yeah. Okay, so those are just the two inert solvents. So again, essentially, I'm gonna draw the bromine up here. This is the concerted mechanism. One of those pi bonds, comes and attacks the bromine, you break the octet, and then it comes back and fixes that deficiency. So we had a 1, 2, 3, 4, 5 carbon chain. So we're gonna go to a 1, 2, 3, 4, 5 carbon chain. The pi bond is between carbons 3 and 4, so that would be here. And what did I do at position 3 and 4? Well, I formed a halonium bridge. So that's what I should be drawing. And it's actually, this is the nicest part, is because there is no stereochem to consider since, it's a pi bond. It's sp2 hybridized. So we can just draw it planar. So that's exciting. Okay, so that's the main halonium intermediate. So it's literally the exact same thing we've seen above, but we just have this extra pi bond because of the extra pi bond here. Okay, and then bromine. So this is the secondary position, and this is a secondary position. So it doesn't matter where we're going to attack, and you'll see why in a second, especially in terms of stereochemistry. So the bromine's going to, let's just say, attack there and open the ring. So we're left with, from the 1 equivalent, now you know why the stereochem doesn't matter, because we're rigid and we're sp2. Okay, we don't have chiral centers there. All right, so this would be, literally, we've seen this. This was halogenation of alkenes. You got this vicinal halide. Here you did the same thing, halogenation of alkynes, except you just had the extra pi bond in the starting material just came for the ride. Okay, any questions? It's really simple. I think it's the same thing. Oh, my bad. I always forget that. Don't forget your substituents. I do that all the time. Thank you guys for catching me. Why didn't the rear attack the other? It could have attacked the other and you would have gotten the same thing. This is not, yes, it would follow anti-addition if it was this, okay, where we had a chiral thing to consider. In this specific reaction, we're never going to we're not chiral at all in any step of this mechanism, so we don't have to consider the anti-addition or a addition or, anti-enantiomers. That's actually the nice thing of this. Yeah, that's the nice part. Yeah. Cool. Oh, light bulbs, Emily. Love that. All right. So that was K. Let's do some more. This reaction is not stereospecific. That's great. And not Regis, and not, yes. You could say that. Yeah. So for alkenes, yes, it is. For alkynes, it's not. For reasons we clearly see. And actually, Lauren, be careful with the regiospecific or regioselective thing, because it could still be, this specific example, it's not. But if I did have a tertiary position maybe here, or actually, let me try and think of one. I can't really imagine a situation that would, yeah, I could. If this was more substituted, like if I had like maybe a methyl substituent coming off here, instead of the proton coming off here, you would attack regioselectively here. Does that make sense? You could still be regioselective. This is just an example of it not being regioselective. However, it's definitely not stereospecific, okay? Maybe that helps you. All right, let's do some more practice. So we're on L. So for L, we are going to draw, looks like a tert-butyl group. Okay, and we are up here, and we are subjecting this to Cl2, and I'm just going to say DCM, that's the inert solvent, and that's 2 equivalents. Okay, awesome. So again, so this is now not a situation where we have one equivalent, we have to do 2 rounds of this, okay? Does that all make sense? That's all it means. 2 equivalents means do 2 times this. So essentially, I'll just draw this really quickly. It's boom, boom, boom. So the product of step 1 is now kind of obvious, I'm hoping. So this is a 1, 2, 3, 4, 5, 6 carbon chain. Let's do a 1, 2, 3, 4, 5, 6. Okay. On 2, we have the 2 methyl groups. And then in between 3 and 4 was where that alkene is going to be. And we know that we formed this bridge there. This is just everything we've already seen before. So that's pretty nice. There's no difference in terms of substitution here. So this is also a situation where we're not reduce selective. Okay. So then we can just, for all intents and purposes, just pick 4 is where it gets attacked. It opens up that ring. And you know that the end product of 1 equivalent of all of this is going to be that, okay? Again, no stereochemistry to consider. This is the product of 1 equivalent, okay? Now you say there's 2 equivalents here. So let's just do the exact same thing again. We know how this reacts. Pi bond grabs the chlorine, we break the octet, and then it comes back down, okay? So now this is gonna be a weird structure. So it actually looks like this. With 2 chlorines there already, okay? And then you have that chloride anion, okay? And it attacks, again, either position. There's no difference in substitution. And you break the ring. So now, somebody in the chat box, why did I say you don't have to worry about chirality or anything like that? 2 chlorines, great. So nowhere, anywhere in this mechanism were we potentially generating chiral centers. So that's the best part about this reaction. There are no major stereoisomers. This is just that, okay? That's it. Awesome. Anybody confused? Like I said, it's just an extension of the chapter 6 stuff we've already seen, just an extra round of it, okay? I hope this is giving you guys some comfort. I know a lot of you guys were panicking, not thinking you'd have enough time, but I told you like that these should be a little bit easier. Okay, so yeah, let's do M. Okay, so it seems like we're getting some questions with that. And let me just check the chat box. Is this stereochem? No, there's no stereochem, Brian. Jada, would we ever have to know the bridge? Yeah, you would have to maybe produce a bridge. Yeah, she might say, draw the second intermediate and this mechanism, you know, displayed above. So yeah, are alkynes not stereoisomers? No, because you only have 1 substituent at either end of the alkyne, and you know, geometric arises from the fact that we have 2, let's just say that. So we have the 2 of these substituents, you know, we assign priority, and that's where the major isomers came from. But when we have alkynes, something like that, there is no difference on either side. So no, there are no major stereoisomers of alkynes. Great question, Priyal. Kelsey, this last step, do you add the previous chlorine? You add the second equivalent of chlorine. So like, do you see here, we generated chloride anion. So this is from the second equivalent, and then that second equivalent chloride anion came in and opened the bridge. It's easier when I explain it. Aw, thanks, Lilas. And Lauren, I have a feeling she's gonna ask about intermediates a lot. Yes, everyone read Lauren's question. I have a big feeling that that's also going to be tested. So I would know how to do that. You guys get my drift. Make sure you guys know your intermediates, like, okay, because that's definitely a very fair question. The halonium bridge. So this is 1 intermediate, the halonium bridge here, and this is another intermediate, a halonium bridge. Okay, cool. Yeah, let's keep going. So 11M, we'll do this last example, and then we'll move on to another reaction. We are breezing through this. Okay, so 11M is going to look like this. Okay, and we're going to subject this 1 to bromination conditions. So this is chloroform. And then step 2, we're going to subject it to chlorination conditions. Okay, so that would be, okay, something like that. So again, pretty easy. I'm just going to draw the bromines, you know, diatomic over here. Nucleophilic pi bond grabs the bromine, that breaks the octet. You start getting a little bit of partial there, remember, so then we're going to come back down. We were 1, 2, 3, 4, 5, 6. So that's 1, 2, 3, 4, 5, 6. Remember that pi bond is going to be between 4 and 5. So 1, 2, 3, 4, 5, 6. Number. I know it's like more work, but it's really so helpful. And we have this kind of halonium bridge forming in between 4 and 5. Okay, so we're there. And then, you know, you have this bromide anion, okay? And there's both secondary, those positions. So we're gonna attack here. Let's just say that one and open the bridge. So the resulting structure is going to be something that looks like this with 1, 2, 3, 4. So it looks like 4, there's gonna be a bromine, and then 5, there's gonna be a bromine, but it's rigid, okay? So there's that pi bond right there. So this is the product of step 1. So product of step 1, okay? So then you have to do product of step 2. So now it's just a chlorination condition. So we have chlorine and chlorine, okay? We're gonna grab here, exceed the octet, and then this chlorine is gonna come back, okay? So we form a new, like, chloronium bridge. So chlorine, so bromine, bromine, and now chlorine is gonna come in. It doesn't matter what position again that it's attacking, opens that bridge. I keep switching colors on you guys. And you get, I'm losing my positioning here. Bromine, chlorine, bromine, chlorine. Cool, right? So it's the same exact thing. We just, instead of doing 2 equivalents of bromine to get 4 bromines adding, we split that up. Now we did 1 bromine and 1 chlorine, and you can do that, and you get these 2 halogens instead. Okay, questions? I think I heard a microphone on mute. Okay, we are gonna do O, because O is a very important question. Oh yeah, so that's another thing. So this one has stereochemistry. Dr. Peterson, most likely, and I'm saying this loosely because I don't know for a fact, she's done this in past semesters, she'll say for this specific question, ignore stereochemistry. Because you would have obviously actually you could do it, I mean, you know, there would be 4 of them, but there are going to be some specific, you know, you'll see on the test, especially going into exam 4, well, she'll be like, oh, you can ignore stereochemistry. Oh yeah, I'm sorry, there'd be 2. Hal, thank you. There'd be 2 because of anti-addition. So I don't, did she put on the key stereochemistry? I don't think she cares about it. Oh, she did. Oh no. Okay, well fine, we can do that. We can come up with that. So basically what you have to think about is there's 2 options. So I didn't think about the stereochem, my bad. I didn't think there were. But let's just say that, let's say the original bromine bridge was, you know, on a wedge, okay? Let's just say that. So that means that we had something like this. Okay, so that means that the bromine is going to have to come in on a dash. Actually, this is so much more complicated than I thought it was going to be because it's rigid. Let me think about that for a second. So it's been a while. Hold on. There's that. And then, okay, so then you get chlorine, that goes away. And then chlorine. Okay. Here's the key step. Okay, I just figured this out. Let me draw this over here. So there is no stereochemistry after through step 1. Okay, so you can all follow that we're here, right? After the bromine addition. Okay, so there's no stereochemistry yet to consider. When the chlorine bridge comes in, now we have some stereochemistry to consider. So I'm gonna draw both intermediates to, you know, this is something where I would go slower on the test. So let's just say they came in on I would draw this intermediate out, okay? Because it's gonna help you with your stereochem. Okay, so let's just say it came as a wedge, but we could have also equally have likely said that, okay, what if it came on a dash? Okay, thank you guys for pointing this out. I didn't know you had to show the stereochem. Okay, and then chlorine, remember, is gonna come in and attack, okay? And it doesn't matter which position, so let's just say it attacks here, okay? And it's gonna push that open. So, because the wedge face is sterically hindered, remember, whatever the bridge is on is what's hindered. So if the wedge face is hindered, that means that the chlorine comes in on a dash, okay, which forces that existing bromine onto a wedge. This chlorine stays as a wedge, and then that bromine stays as a dash, okay? So that's the first one, okay? Then the same thing can happen over here. So we attack here and push that open. So we get a structure that looks like dash chlorine, wedge bromine, wedge chlorine, dash bromine. And those are your 2 main structures, all right? Those would be the stereoisomers. So in terms of, you know, figuring out when to start considering the stereochem, you can go through step 1 and not consider anything, and then consider it in step 2, okay? I know. Here, let's take like a minute break. I know, I'm throwing a lot at you, but I really think that this is all kind of just an extension of 6. Like we're just kind of, you know, applying it a little bit more. We do have, let me see how many more reactions. Okay, we have 5 more reactions. They're not that bad. We're gonna try and finish, okay? I honestly wish the exam was next week too. I am shocked that it's so soon. Okay, sorry. But they're quick, I know. I don't wanna scare you guys. Okay, so just take a break, you know, take a lap around your room, wherever you are, like open a window. It's really nice out, like, okay. I mean, the fact that you guys are here shows that it's not going to be like you guys aren't going to be spending so many more hours studying this, you know, like the other people are. Like you guys definitely have a good foundation by watching these videos live and getting your questions answered. So you're definitely better off than the rest of the class. All right, let's just do a quick example, important, and it's O. Okay, so we're on O. Okay, so we have this structure and it looks like a vinyl substituent. There's a lot of steps, but it's important because this is a key question that I'm going to talk about. Yeah, let's push through, everybody. I agree. I like that mindset. Okay, let's just all push through, everybody. I'm in it with you. Listen, do you think I want to be sitting here? Like I have my own classes, but I want to make sure you guys get it. So we're gonna do this for you guys. Okay. Okay. So. All right. So here we are. This is going to be a very, very key question. I would know this inside and out, okay? And the reason that is you're gonna have something called a synthesis problem, and I don't know if you guys have seen those yet, but it's gonna be basically you have a starting material, you have an end product, and you need to basically use however many reagents, we're not gonna tell you how many, and we're not gonna tell you which order to complete that chemical transformation, okay? But however, since you're very early on in your orgo journey, you guys don't know that many things. So there aren't that many pathways that we can test you on. This is a very obvious pathway that is most likely gonna be one of your synthesis problems, okay? So I would know how to do this, you know, chemical transformation, okay? So if you're starting from an alkene and you want to extend the carbon chain, okay, so let's say my synthesis problem looks like this, and this is why I'm going over it. Let's say I start here, and somehow I ended up that, which is a very characteristic question every year on synthesis, you know, going from an alkene to an alkane. And to do that, you would do these series of steps, okay? It's not memorizing. I know you could memorize it, but it's not going to memorize it because it's going to make a whole bunch of sense, okay? So let's just say this was like I have a target, right? And my target is going to be, here. Actually, I don't want to go there yet. We'll go to synthesis in a little bit. But basically, let's just follow these steps. So the first step is going to be bromination, okay? So we know we're going to get, you know, something that, and I'm not going to really consider stereochemistry until the end. So we basically have bromine here, okay? So that's kind of obvious. Then we know sodium amide and the 3 equivalents is going to form a terminal alkyne, okay? So basically what that's going to do is form a structure that looks like this. So it's 1, 2, so 1, 2, okay? We remove that final proton, okay, in the 3rd equivalent to get the acetylide anion, okay? Then in step 3, it looks like we add 2 carbons, 1, 2, so it forms 1, 2. And then it looks like in step 4, oh, I forgot the 2 equivalents, my bad, 2 equivalents. We're adding 2 equivalents of bromine to this, you know, structure. So essentially we have 1, 2, 3, 4. So it's 1, 2, 3, 4. And on positions 1 and 2, we have 2 bromines. That's the end product. Okay. So you guys should be a lot quicker now when you're starting to see multiple steps. Okay. And this is a very characteristic thing in synthesis, because if you have an alkene and you want to add extra carbons, we only know one reaction that does that, and that's acetylide. So so you have to stop, okay? Stop in your head and you have to ask yourself, how do I go from an alkene to the alkyne? Because I know I have to add carbon somewhere, okay? Well, the only way to do that is to add, bromines to brominate it, and then I can do the double Dehydro Halogenation reaction to form that terminal acetylide anion. And then you attack with a haloalkene, add the carbons, and then you can just do whatever you want after that, okay? This is a very characteristic step in terms of your synthesis, okay? I would really know this. This is really important, and we'll see more examples of that. Okay, I'm all over the place. Let's move on to the next reaction. Let's keep going. Okay, so this one's easy, guys. This one's easy. This is what we've already seen this one before. So this is hydrohalogenation, okay? Yes, I can go back. This is, so, oh, I lost that paper. Where was I? I lost it, guys. Where'd it go? Oh, it's right. Okay. That's where we were. Okay, so this one we've already seen before. I hope you guys will recognize this. What does excess mean? Okay, that's a great question. XCS equals excess, which basically just means a lot. So like, we've seen like, let me show an example. Like, I'm looking at this page right now and I see we have HI 2 equivalents. Okay, so that's 2 to 1. If you were to say, this and it's HI excess, that basically means like, throw out a number, 100 to 1. Like, it just means a whole bunch more than you need, basically, okay? Just a lot. And that doesn't really mean anything. It just means you react as many times as you basically can. That's all it means. I know you guys are all complaining, your head hurts. I feel bad. Hydrohalogenation, okay? So you guys know this one, okay? So essentially, we've seen this before. I already demoed it for you. So this is the example that we're looking at. And we're subjecting that to HI, and we're doing 2 rounds of that. Easy. Grabs the proton, generates the iodide. So you are going to get a carbocation at the more substituted position. So look, 1, 2, 1, 2. And clearly, the more substituted position would be the benzylic position. So I know it looks weird, okay? It's on the pi bond for sure. There's no proton there, okay? So we get a carbocation there. Then iodine is going to come in and attack. So this is the product of 1 equivalent of that adding in, okay? So then you subject this same reagent to HI. Like, look how easy this is, guys. It's not as bad as you think. And we're going to generate a carbocation again at the more stable position. So that's right below the iodine or the benzylic position. And then you have that second anion of iodine coming in. And this is the product of 2 steps going in. And it's achiral. Okay? I don't think this is too difficult. You guys have seen this a million times. The only thing is now we've added a second round of it with the extra pi bond. Okay, and then you can see in R and T, you can change it. Instead of 2 equivalents of HI, you can do 1 equivalent of HI and then another equivalent of HCl. Okay, bye Keisha. Yeah. Okay, so that's that. All right, so I'm not even going to do more examples of that. I think this is like enough of that reaction. Hydrohalogenation, pretty easy. Okay, so let's move on to the next reaction. Okay, so these 2 are in tandem, and then we have one after that. Okay, so reaction 15, this is acid catalyzed hydration. Again, and this one's nice. There's no mechanism, I promise. It's getting easier. Acid catalyzed hydration of alkyne. There's no more mechanisms we're going to talk about. Okay, just predicting the products. So acid catalyzed hydration of alkynes resembles acid catalyzed hydration of alkenes. So you guys know this, and you form an alcohol, right? You're doing the exact same thing with these alkynes, okay? So let's look at U. Okay, so essentially we have this terminal alkyne, and we're subjecting it to mercuric sulfate, okay? Mercuric sulfate, sulfuric acid, and water, okay? So in the sense, it's acid catalyzed hydration, but you have, and this is also sometimes called oxymercuration of alkynes, because, mercury, so if you're ever confused of what something does, mercury was used in oxymercuration of alkenes. We've seen that. Step 1 was HGOAC2, THF, and step 2 was sodium borohydride. I think there was also water up top here. So this also did the same chemical transformation. Remember, there were no rearrangements, but it does the same thing. So again, this is just oxymercuration, a little bit different in terms of their reagents, but oxymercuration of alkynes. Okay, same exact thing here. Okay, so what you're going to do is you're basically adding an alcohol to the more substituted position of this alkyne. Okay, so here we have a primary and here we have a secondary. So that's obvious, and let's add it to the secondary position. Okay, does that make sense? We are doing the exact same thing that we did with oxymercuration, which just means add an alcohol to the more substituted position. we are adding an alcohol to the more substituted position, okay? So this intermediate is called an enol, okay? And I'm adding another thing here, but don't freak out. We are going to go over the mechanism in Orgo 2, and we're going to talk about reactivity in Orgo 2 of why this happens. But what happens is there's essentially an equilibrium shift, okay? And we want to favor a structure, okay? And it's related via resonance, and we don't need to go through that. It's not tested, so don't worry about it. It's the keto, okay? So this is enol to keto tautomerization, okay? And it's extensively covered in organic too, but for all intents and purposes right now, you generate an enol, and you just need to know that it does something called tautomerization, okay? And they're isomers of each other, so these are both isomers, okay? And we prefer this keto version because the carbon-oxygen bond, this bond, is stronger and stable than this arrangement, okay? That's all you need to know now, okay? So it's the same exact thing that we saw before. You're adding an alcohol to the more substituted position, but this is an enol arising from the alkene, ene, and alcohol, al, so that's enol, and it prefers this keto form because we just have a stronger, more stable bond. Just go with that for now until you go to Orgo 2, okay? So the product of this reaction is this, okay? This ketone, okay? There is no mechanism for this, Mary. Nope, 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 no mechanism. This is nice, just know that, okay? We're gonna do more practice of this, okay? So let's go to V. So V looks like this, and I want you guys to start getting some examples of this, okay? So HgSO4, H2SO4, water, okay? So again, we know that we are adding an alcohol to the more substituted position. Okay, so where is that? So here we clearly have secondary. Here we have secondary. So this is a situation, because there is no symmetry, that we actually get a mixture of products, okay? Because there's both secondary positions. So essentially, let's call this 1, 2, 3, 4, 5, 6. So that becomes 1, 2, 3, 4, 5, 6. And then between 3 and 4, 1, 2, 3, 4, we have a pi bond. On 5, we have a methyl group, okay? So essentially, we could have the alcohol adding here, or we could have had the alcohol adding up there. So we could form the enol up here as well, okay? And then both are going to shift in terms of, equilibrium. We don't need to talk about the mechanism, to the keto form. Okay, so just draw a ketone where that alcohol is. That's one. And then and that one. So these are structural isomers of each other. Okay. Why do you add a carbon in the chain? Did I do that? Did I do that? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Oh, don't ask. I don't know. I added a carbon by accident somewhere. Let me redraw these. My bad. 1, 2, 3, 4, 5, 6. Here we go. That looks better. And this was between 3 and 4. Yeah. So the enol could have been here, or the enol could have been here. And then you just draw the ketones where the alcohol was. So draw a ketone down here. That's one. And then draw a ketone up here. And again, no stereochemistry because they're ketones, sp2. Thank you, Hal, for catching that. I didn't see that. Okay, so again, nothing crazy. There's no mechanism. When there's no difference in substitution, consider both products. This is called enol to keto tautomerization. So enol, I'll read it out, to keto tautomerization. I literally normally go into the theory about all this, but we have no time and you guys do not care because it's not tested. So just know that the ketone is more favorable because it has a stronger stable bond. That's it. That's all I'm gonna say. Okay, that's that guy. So let's move on to question 4. Okay, so this one wants you to draw the enol and the keto tautomer. So okay, so we want enol version and the keto version. So we have a primary position here, a secondary position here. So the alcohol is clearly going to add on the secondary position. So that's a 1, 2, 3, 4, 5, 6 carbon chain. 1, 2, 3, 4, 5, 6 carbon chain, and in between 5 and 6, the enol should be adding there, okay? And the enol tautomerizes to the ketone, so all you do is put a ketone there. And that's that, okay? So that's how you would fill that in, okay? And then let's try another example. So let's try this one. Okay, so we're here. So again, there's a secondary, okay? There's a secondary position there. And then here's also a secondary position, okay? So in terms of substitution, we're just talking about substitution. They are the same. Oh, and I think there's a question going on here. Yep, okay. So essentially you get, actually I think on the key, does she only have one product? I feel like Brian, you have the key out. Does she have one product here? 2, good, that's what I thought. Okay, so we're not thinking, and this is why I said this, we're not thinking carbocation instability, like clearly we see a benzylic position here, and here there's just a plain secondary. We're purely only saying what is the substitution. So there's a secondary and a secondary, so they're both equal in terms of substitution pattern, so they both get enols at those positions. So 1, 2, 3, 4. So essentially, I'm just going to redraw this benzene to look like this. 1, 2, 3, 1, 2, 3, 4. 1, 2, 3, 4. And at the, we could have the enol here, or we could have had the enol down here. And then both of those enols tautomerize to the ketone up here and down there. Okay, do you guys kind of get that? So there's no mechanism, that's great. You know, it's the same thing as oxymercuration, where you add an alcohol there, and then you just go to the keto, okay, always. Is one more stable than the other? These structures, no, I can't really think of anything. Okay, cool. So that's it. Let's move on to the next one. So, this is clearly oxymercuration. So you could, if you're thinking, oh, is there a hydroboration version of this where we do the less substituted? 100%, and that's the next one, okay? We're almost done, I promise. How much time are we at? Oh my God, we're so long today. Okay, so thank you guys for sticking it out. I appreciate it. You guys are gonna rock it. It's gonna pay off, okay? So now this one is hydroboration. Oh, you guys are sweet. Hydroboration, okay? This is hydroboration oxidation, okay? So we clearly saw the oxymercuration, demercuration version of this. Now we're gonna do the hydroboration version of this, okay? Again, no mechanism. We're gonna talk about some key points, but other than that, it's just pretty easy, okay? So the reagents are different now. So, maybe I'll just draw a comparison to, alkenes, and we saw we had borane, okay? We had THF, I believe, and then 2 was sodium hydroxide and hydrogen peroxide. And what that did was it gave us the alcohol on the less substituted, or this was anti-Markovnikov addition. Okay, I think you guys saw that, Markovnikov. I'm spelling like crazy, anti-Markovnikov, something like that. So now we kind of changed the reagents just a little bit, just like we saw with the acid catalyzed version. So we have this kind of, you see boron there, okay, so that should be a big hint, okay? THF is still there. And then 2, oh look, everything is the exact same, okay? So this is clearly a hydroboration example. Okay, did you see that? The only thing that changed is this reagent. So this is disec-isoamyl borane. Don't ask why I know that. And I just know it as Sia. So you guys know the singer, Sia, that sings Chandelier and a whole bunch of great songs. Anybody watches, I think it's, what is it? Not Amazing Race, it's Survivor. She personally gives like $80,000 or something to like her fan favorite. And it's like aired on the finale. I don't know if any of you guys know that. She just like loves the show so much. She's like this longtime fan of Survivor that every season finale that's live, she'll be like, this is the Sia Award and here's $80,000. Yeah, I don't know. It's really funny. So now you guys will remember, Sia is hydroboration. Okay, think about hiding in the forest, I don't know, for Sia, or when you're doing Survivor. I don't know, something to remember it. I'm helping you guys. Okay, so we're gonna add an enol, okay? An enol on the less substituted position, okay? So clearly now when I have a primary versus a secondary, we're gonna add the enol on the primary position. Okay, so what that looks like is something like this. So 1, 2, well, let me count. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. Okay, so between 5 and 6, we're gonna have the enol and we're gonna add it to the less substituted position. Do you see that? So a consequence of adding this to the less substituted position is we're not going to form a ketone, but we're going to form what functional group? What do we think? Similar to a ketone. Somebody in the chat box. Aldehyde, perfect. So because it's not internal anymore, which would have been a result of the previous reactions, these are terminal. So for the most part, it's either aldehydes or ketones. Okay, cool. So this would be your main product. Okay, same exact thing. Okay, so just a mechanistic point that I want to mention is the same thing when we talked about, remember, there's a BH, this is borane, okay, and then this is, okay, same exact kind of thing going on. And if you were to cut through the middle, we said there was a more sterically hindered fragment and a less sterically hindered fragment. So this is the more, this is the less. Same type of thing is going on. This isoamyl is kind of, I don't really know the structure, but I think it's something like, you know, something, I don't really know the exact kind of skeletal structure, but you can see there's clearly a more fragmented side and a less fragmented side, and it's going to do the exact same kind of like steric alignment. So you get the BSIA2 fragment over here, and then you get the H fragment over there. Okay, but you don't have to know any of that for really producing the products. Okay, let's do one more example of this. So I'm just going to jump down to DD down here. It looks weird, right? So we have this wedged alkyne. That's bizarre. And doing the, I'm just going to say, you know, double line for the same conditions that we've had. So think about, you know, this is a looks like 2 carbon substituent. So let's just do ethyl. Okay, 1,2 carbon substituent. We're going to have the enol between 1 and 2. And remember, it's the hydroboration. So it goes towards the end. Okay. So the resulting, let me just draw the stereochem. Resulting substituent is an aldehyde. Okay. And that's that. So I think you can see like these weren't as much work as you thought there was. Okay. It's pretty easy. All right. I think that's enough. So let's move on to the last few reactions we've made it, everybody. These are pretty easy. Okay, and it's really one reaction, but we have 3 subsets, 3 types of them in there, so don't worry, don't freak out. Okay, and we're almost there, guys. Okay. So now we're just talking about reductions, okay? So we already saw, so this is now catalytic reduction. So you guys see, they're all the same reactions for the most part that we saw in, chapter 6. We're just extending them now to this situation. So we are on EE, okay? And so we have this example, okay? And, oh, did I skip a, oh, here we go. There we go. And we're doing this to H2 and platinum, okay? So if you saw it before, remember we had examples like this, and we're like, okay, the H2 and platinum is going to reduce all of the alkenes of unsaturation points and saturate it to form, a plain alkene. And we said that if there were, if there were substituents here, let's say an ethyl group, then since the H2 is added via syn addition, you have to consider the major stereoisomers because that would be the product of H adding on a dash, H adding on a dash there. And if it added on a wedge, that forces this ethyl group back. Okay, so just those were the key points that we were talking about from chapter 6. So the same thing is going to happen here. So what's going to happen is all of these. So H2 platinum is the strong. So I'm going to write this strong reducing, strong red. Okay, so every single pi bond, every single one, it doesn't matter how many, and it doesn't matter what type, either alkene or alkyne. Every single one is going to go back to the alkane. Okay, so basically the resulting structure is 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. Done. Okay, everything. Okay, that's it. No mechanism, no nothing. So F. So yeah, fun, really cool. So here we go. Now we're subjecting it. Okay, so let's just say I'm doing this as well till maybe H2 and nickel. I changed this. This isn't FF. H2 and nickel. Okay, again, that goes away. So 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. And that's it. I wrote strong red because you're going to see there are weaker ones coming up in a second. And strong ones reduce everything. Weak ones don't. So we're going to see what's the difference there in a second. Okay, so now there's 2 other variations. So this one's the obvious one that we knew before. Okay, and now we're going to talk about the 2 new ones that we haven't seen. So other reductions that are kind of still under this category. So other reductions. So we know one is H2 and platinum or palladium or nickel, any of those, okay? The second one we're going to talk about is H2, but not those catalysts. We're going to call it Lindlar's catalyst, okay? Lindlar's catalyst. I swear we're almost done. Like seriously, this is the last step. H2 and Lindlar's. And then the last one is going to be sodium, but with this degree sign, okay? It just means pure, that just means pure elemental sodium. Not like salt, it's not like table salt. This is like pure elemental, like explosive reactive form, okay? So that's that, and dissolved in ammonium liquid. Okay, so those are the 3 reductions that we're talking about. This one, we already know, it's really easy. It reduces every single thing to an alkane. With this one, H2 and Lindlar, let's just take FF because I think that's the example of it, okay? H2 and Lindlar is not gonna, it's a weaker, so weak reduction. So it's not gonna convert the alkyne. So you can imagine, we can go from probably alkyne, okay, to, we can do 1 reduction, and we can go to 1, 2, 3, so 1, 2, 3, to alkene, okay? And then you can do another reduction, and then you could go to alkane, right? Oops, okay, so alkane. So the strong reducing people, so the strong reducing agents go all the way to the end product in 1 step. So this is strong reducing. So that's like H2, platinum, any of those guys, okay? But what's gonna happen is if I use a weak one, this is what happens if I use the weak conditions. I only stop at the alkene. So that's kind of the theory behind it. Strong is always gonna reduce all the way to the alkane, but any of these weaker conditions aren't gonna go all the way to the end product. It's gonna go here, okay? So what specifically does Lindlar's catalyst do? It stops at this alkene, but specifically it's a Z alkene. So Lindlar is Z, okay? Lindlar is Z. So like Lindlar's, like I just say it's Lindlar's, like, and that's a Z at the end. So always remember to make a Z alkene. So essentially it's 1, 2, 3, 4, 5, 6. So between 4 and 5, I need to be in the cis conformation. So ready? 1, 2, 3, 4, 5, 6. Okay, so 1, 2, 3, 4, 5, 6. Oh, did I do that wrong? Oh, it's between 4 and 5. My bad. 1, 2, 3, 4, 5, 6. My bad. 1, 2, 3, 4, 5, 6. There you go. So that's your end product. You get specifically this Z alkene. Okay, you reduce it to the Z alkene, H2 and Lindlar. Okay. And then the sodium amide one, that's the last one, is an example. I guess it's just GG. Yeah, like Z geometry. Yeah, that's what we're talking about. So notice how, with respect to this horizontal line, they're both on the same side. Okay, so let's take the last example, and we're done. Hallelujah. All right, GG. So we're here. We are here. Okay, so we're there. Okay. No, great question. Okay, Lindlar's catalyst cannot reduce an alkene to an alkane. It only goes from alkyne to alkene. Good question. It's quite literally, all you guys know at this point is that to there or that to there. Oh, sorry. That to there or that to there. Okay, those are the only 2 you know. Okay. I'm not doing HH because that's like an obvious example. That's like just reducing everything in there. I just wanted to do this one example of sodium amide. So sodium amide, and I don't care about the ozonolysis stuff. So basically, that's going to convert, instead of the Z alkene, this is another weak reduction reaction, okay? And this is going to convert to the E alkene, okay? So the E alkene would be, so there's 1, 2, 3, 4 carbons in between these 2 cyclohexanes. So 1, 2, 3, 4, and then the ring. So this is between 1, 2, 3, so 1, boom, okay? And this is the E alkene. We just covered all of chapter 7 in an hour and a half. All right, let's see, just to confirm, if the molecule had both an alkyne and alkene, the resulting molecule with Lindlar would lead to a molecule with 2 alkenes. That is correct. But the Lindlar one, the one that wasn't already in the alkene. So let's just do this. So that, and you want to subject this to H2 and Lindlar. This is going to stay E, okay? This is going to go to Z, okay? So that's actually a great point. So 1, 2, 3. So 1, 2, 3. So that's the Z part. 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. So 7. Okay. Z and E. Great question. All right. Tomorrow, I'll send out an announcement definitely tonight about when I am going to do this exam review. What does that entail? We're really going to just hammer down all of the synthesis problems and the critical thinking questions, and also talk about, we never talked about a reaction coordinate diagram. So we have to go over those 3 main things, okay? So what am I going to suggest you guys do, like, from now until tomorrow? I would basically do every single predict the product, every single mechanism, every single just like question that's in the student workbook up into the critical thinking / synthesis section, and that'll be good for you guys tomorrow. Okay, I'm going to try and upload this video, both of the Monday video and today's video, up onto YouTube soon. And yes, Brian, please remind me tomorrow to do the intermolecular reaction. And Jada, I'm trying to do it around 3, but I don't know because I work at the Orgo lab and we get out at different times. So literally, it might just be like, it's going to be around there. I just don't know if it's like 3 or if it's going to be 3:30 or something like that, but it's definitely going to be around that time. Okay. With that, you guys definitely deserve a break. Like, I don't know, go get coffee, go get Chipotle or something, and take a break and revisit this in like an hour or 2. Okay. All right. And I will see you guys tomorrow.